Head movement is a compelling form of input modality because it affords hand-free and nonverbal interaction. However, not all types of head movement are the same. We turn our head to see what's around us, and we use head gesture to express ourselves. There are fundamental differences between the type of movement used to direct visual attention and those used as gestural expressions. We refer to them as head gaze and head gesture. They are both of utility, but differ in affordances. Hi, my name is James, a PhD student at Lancaster University. If you'd allow me, I'd like to share with you how we classify these type of head movements using machine learning, and how by treating them as distinct modes of input allows for more seamless interaction with simpler head movements. This work is done in collaboration with my colleagues Joshua, Ludwig, Anam, Per, and Hans, with contribution from Dominic. But first, let's play a game to experience how head movement allows for hand-free interaction. There's a list of animal cards in front of me, avians and mammals. I can swipe them to sort them into categories. Avians to the left, mammals to the right. Hey, I recognize that dog. That's my friend Dominic's dog. I want to look at it. Oh no, I didn't mean to swipe it. I turned my head only to look at it. Now I made a mistake. This is annoying. If only we can tell when the head movement is a gesture and when it's a part of gaze. A lot of times, gestures have to be designed to be exaggerated movement to avoid accidental activation, or avoid it altogether. If we can distinguish head movements that are gaze-driven and head movements that are expressions of the head in its own right, we can treat them as distinct modes of input and allow their use in tandem. We call the type of head movement that is gaze-driven head gaze. Head gaze supports the eyes in directing visual attention to objects that are not already right in front of us, and to keep the eyes within a comfortable eye-in-head position. In contrast, when we move our head independently of gaze to describe a gesture, then it is the head that leads the interaction and the visual system that adapts, making it possible to use head movement as means of expression without disrupting vision. We call this type of head movement head gesture. Head gaze is the type of head movement driven by gaze to support us directing visual attention, while head gesture is independent of gaze and used as gestures. The classification of head movement as head gaze or head gesture not only reduces false activation, it allows us to leverage the two types of head movement in more improved and novel ways. For example, if I have two displays, each contains a deck of cards, the one I'm attending to is the main display. I can use head gesture to swipe cards in it, and when I look over to the other display, a head gaze is detected. Instead of falsely activating a swipe, it centers the now attended display, which allows me to use head gesture to swipe cards in it. I can use head gaze to switch between multiple displays, and head gesture to complete actions only in the attended display. Therefore, the classification of head gaze and head gesture allows multiple head-based systems to coexist without accidentally triggering each other. Another benefit could be the seamless switching of interaction modes in the same application, depending on the user's current need. For example, switching between gaze pointing and head pointing for ergonomics and the precise control of the cursor. This is an adaptation of the bimodal gaze technique by Sidenmark and colleagues, who inspired us in this work. Initially, the cursor, shown by the white square, is controlled by gaze. Due to tracking inaccuracy, the cursor is offset from the true gaze, shown by the red dot. When the cursor lands on a card, its information is displayed. Now I want to look at the Shih Tzu dog, but the eye tracking is not accurate enough. A head gesture switches to head pointing to allow precise control of the cursor, and head gaze switches back to gaze pointing. Let's take a closer look at head gaze and head gestures. and what challenges we need to overcome to classify them. When I look at a target, my eyes move first and acquire the target. Head is slower, and most of the head movement happens while gaze is already on target. As the head catches up, the eyes compensate for the head movement to fixate on the target. This is observed as opposite movement of eyes and head, known as the vestibulo-ocular reflex, or VOR. You can see this on the plot here, where the blue eyeing head angle and the orange head angle move in opposite directions. The head movement here helped us direct the visual attention to look at the target, so is the head gaze. Now I use head gesture to move the ball into the black hole. The same relative movement of head and eye is observed during head gestures, where the eyes compensate head movement to stabilize vision, making it difficult to distinguish gestural from gaze-driven behavior. We explore a machine learning solution and design a task to collect head gaze and head gesture data, while automatically labeling the movement phases for training. First, participants gaze shift to acquire a target, with associated head gaze movements. Then they perform head gesture to direct the ball into a hole. We vary the sensitivity of how head movement is mapped to the movement of the ball by varying the control display gain in order to draw out head movement of different amplitudes and velocities. We employed common features for eye and head-based classifications, including shape-based, noise-based, spectral-based, correlation, and timing-based features. To capture the temporal history of participant behavior, we included the feature vector from the previous 1 second, sampled at regular intervals. We used an extreme gradient boost or XGBoost classifier to classify head movement into either head gaze or head gesture. We called our system HeadBoost. Its global offline performance achieved an F1 score of 0.89. HeadBoost is able to classify very small head gestures and detect the onset of head gesture earlier than the heuristic baseline. We calculated the feature importance and report no single feature is solely responsible for classification. Rather, a combination of head-based and temporal features contributed to predicting the type of head movement. And finally, to demonstrate HeadBoost's online utility and practicality, we implemented the card game application and showed that the classification of head gaze and head gesture enables designers to create a more seamless and natural way of interaction, using simple head movements while avoiding false activations. In this work, we make 3 main contributions. We introduce the fundamental differences between head movement driven by gaze, head gaze, and those independent of gaze, head gesture, to make case for their use as distinct modes of input. The stimulus and the task design is able to separate head gaze and head gesture for automatic labeling of head movements. We developed HeadBoost, a novel classifier, to classify head movement into head gaze and head gesture. It achieved a person-independent F1 score of 0.89. We further demonstrate its feasibility and practicality with 3 applications. We elaborate more on our ideas in the paper. If you're interested, we would love to hear from you. Thank you for listening.